listen, I'm Gillian Hughes. This is my colleague Gunny from TechWorks. I head up the design network at TechWorks, which has just been relaunched 6 months ago. Gunny heads up the Automotive Electronic System Innovation Network, and I would just like to thank you all for coming to my second event, and hopefully I'll see you at much more. Right, thank you.
Thanks, Gillian. So good morning, everyone. I'm Gunny Dariala. Gillian's introduced me. This is a really special event for us. We've been deliberating around FPGA and understanding whether there's an appetite for it. So Gillian's put a lot of work in getting audience together and speakers. So I think it's going to be a very exciting event today. And judging by the turnout, there's definitely interest in this space. So I think that's a really important thing to acknowledge as well. So prototyping systems using FPGA. I'm just going to talk a little bit about TechWorks so you can see the positioning of the networks and how this all fits together. So just an introduction to TechWorks. Is there any way we can go ahead this? There's minimization.
To take us 2 seconds. Yeah. Technology. Apologies.
Who don't have anything to do with it?
Just 2 seconds, Gunny.
The TechWorks is all about, as it says, empowering UK's deep tech companies to innovate and collaborate. We deliberately choose the word deep tech because it's something that distinguishes where we sit against other organizations in this space. And I can honestly say we're totally passionate about this. Gillian and I have talked about this earlier today about, if we were doing this for organizations, we might be being paid more.
I'm just going to move the cursor away.
We have about 300 members all in all, and we are deliberately aiming to bring companies and especially engineers together and how we can find better ways of working together. Great. Yeah, I'm going to pause there.
This is the entertainment part, right? Got to have fun.
Oh, I mean, we're getting all the things that go wrong out of the way, aren't we?
Yeah. And so just maybe the points to the bottom line, through grassroots engineering collaboration. For me, I say, people really know what they're talking about down at the application level of what we do. And then bringing that through thought leadership, advocacy, talking about the things we need to do in the UK and how we keep building the presence in the UK for what we're doing. That's really important. So this event is an example of the sort of thing we do to bring companies together. And what we do, so I won't go through it all in any level of detail because I know we've got a lineup of speakers, but you can get an idea of the sort of things we cover, everything from the cross-industry, cross-sector collaboration, which this is, again, an example of. Our conferences are really important because they really drive a lot of interest in terms of the trends, the roadmaps, and the future of electronics in the UK. Projects, that's something that we've picked up over the last 3 or 4 years. We're really keen to develop and build collaborative projects. Have had a number of successful projects that have been out of the collaboration. One was Escape, which was all around end-to-end supply chains for power electronics. A £20 million project that was funded by Innovate UK. And so we're very supportive of that. And our role in that is around project management and or industry engagement, dissemination type activity as well. So TechWorks itself is the umbrella company, that's the limited company. And under TechWorks sit 6 networks or communities. And we very proud to have these, and you can see some of the members in those organizations, in those networks that sit within that. So Gillian heads design, right? So that's the relaunched new network around semiconductor systems design. And it's one of the things, again, we see lots of, I'd say, hidden talent in the UK that we need to bring forward and amplify. NMI was the original name for TechWorks. Actually, it's been around for nearly 30 odd years. And NMI now looks after the semiconductor manufacturing and the supply chain elements of the industry. AESIN, I had AESIN, so AESIN is the Automotive Electronics Systems Innovation Network. And again, that's the application level. So everything that happens I'd say the really deep down in the deep tech in itself manifests in an application, and that's where AESIN sits. It's really about how we bring it to the automotive systems space. IoT Security Foundation, that's led by, so I should have said NMI is led by Adam Wood. IoT Security Foundation led by John Moore, and many of you may well know John. So that's been going strong for a number of years now around the whole IoT space, a lot of work around guidelines, standards, and best practices around security. TechWorks AI is actually another one of our new networks, recognizing that we're shifting rapidly to this world of AI, but actually it's the Wild West, it really is, and so understanding how you use it, how you deliver it, how you make it trustworthy, how you bring diligence behind it. So the whole thing around TechWorks AI is to bring this engineering excellence and engineering thought behind the application of AI. So that's run by Gareth Richards, who's one of our new colleagues as well. And Power Electronics UK, again, it's been in and around for a long time. At the moment, it's being supported by Paul Taylor from Dynex. And again, that's a cross-network and a cross-sector view of power electronics. And its main role is around advocacy and pushing the need for power electronics competence in the UK. So that's about it, really. So that's a summary of TechWorks. And we're going to go into talks now. Fleming's our first speaker, so I'm going to ask Fleming to share his screen, and then we'll take questions at the end.
Yes.
Yeah, and then we'll relay them back to Fleming if we have some questions. Thank you very much, and enjoy the day.
Good morning, everybody. Can you hear me okay?
Yes.
To stop sharing, I guess. You got your mouse? There.
Hope you get it.
Fleming, would you like to share your screen?
I'm trying.
Okay. Okay, great. Okay, it's all good.
All good?
Yes.
Good morning, everybody.
Yes.
I hear you've had lots of fun with registration. So unfortunately, I'm not there because I had other pressing issues, like saying hello to my granddaughter. So I'm here to talk about budget prototyping on FPGAs, and I only got sort of 8 to 10 minutes, so I'm going to do it very, very quickly. And then my colleague Bradley is around somewhere with this lovely piece of board as well, so you can go and ask him about non-technical details, and I can then answer the technical details. I'm still around. So just 2 seconds about Sundance. So I've been running Sundance for what comes up to about 36 years, and we've been developing and building electronics ever since. We do everything internally. So we design our own boards and we build our own boards. It's all done on a shoestring operation, as much as that we're not set up to do thousands and thousands of boards. So we've done prototyping on FPGA since '93. So this board was our first board. And some of the numbers which are quite interesting to look at is the number of logic cells. So when I skip through the generations we're doing, you should just watch how the number of logic cells is going up. So this was done for an FPGA system, or a front-end system for PCs and for DSPs, etc., and customers implemented camera link interfaces or other video interfaces. So we skip forward about 2005. This was another platform we developed, which was used by TI for their DSP evaluation. So TI went from having a single core in a single processor until they want to have a multi-core. So this was a development platform which was simulating how TI could see multi-core DSPs. Got a very, very big FPGA in the middle, and that was what was handling all the intercommunication. So look at the cells. So 2012, we got involved in another project, and this is again using a fairly large FPGA. But the idea was to be able to combine and compare two different implementation of an ASIC effectively. And this was done for an EU project called FlexTiles. So the idea was to do different implementation in different part of the two different FPGAs that were all identical, and then see what was the best implementation. The idea for this was to do a 3D chip. So this was the prelude to what's happening now with people building like stackable chips. So this is a coin board. It's a very, very low cost board. I don't think we managed to get one to show around today, but there's a few others which Bradley got on his desk. And so that's got a semi-large FPGA and lots of IOs. So this is one I think we did manage to bring along, and that's enabled a potential use case for designing your own carrier board and then add a very, very big FPGA. And this one includes ARM cores as well. So the numbers of FPGA cells goes up and up. And this is the one I really want to talk about, because that's our new mega FPGA for prototyping. So we picked the largest microchip we could get hold of, and then we added we actually got 5 of them, but one of them is the master, and the other one is or the 4 other ones are slave units. And the cost of this is about £18,000. And the reason why I mentioned that is because you'll see a little bit later that things can get very, very expensive. The concept of this is that we have 4 implementations of identical FPGAs, and then the idea is either that you can implement your prototyping on the different FPGAs, and you can try and swap them around, and you can compare them, or you can use them all together in one big FPGA block. And then it's controlled by the RISC-V core. So the multi-core version of the ProtoFi has got sort of 5 RISC-Vs. And then these are just a slave. So these FPGAs are not as big as the one we can get from AMD and Altera, but they're a lot less costly, and plus they also take a lot less power. The interconnectivity, so the master controller have a number of input outputs to give like kind of a PC lookalike, and it will run a Linux core as well. So you could do a Linux system beta on this as well. And then these are the 5 connectivity. And we have an awful lot of IOs. And there's both memories to the FPGAs, but there's also a number of IO boards which are connected to the FMC connectors. So the reason I mentioned pricing, because obviously what we're trying to do is, and these are our very, very big competitors. So what we're trying to do with this platform is enable small scale prototyping. It is not as listed of all these our competitors, which are incredible big systems and supported by lots of engineers. But these platforms are designed for a low cost FPGA prototyping. That was my 8 minutes, or probably even less. So I'll leave you with that, and questions if possible, or you can just carry on running the show because you're so much delayed. Thank you.
Bear with me. Thanks, Fleming.
You're welcome. Have a good event.
Ran out of USB ports in case you can't work that out.
Oh, amazing.
Thank you.
Thank you very much. Yeah, got 20 minutes. Oh, Jesus. I'll just set myself a little timer so no one do. Hello everyone, I'm Rob Taylor. I'm the CTO at a company called Chipflow, and let's see if this works. And the talk I'm going to give to you today is on fast FPGA and AESIN prototyping with Python for automotive and industrial. And I also like to call this one chip on my shoulder. So I've been doing embedded systems now. I mean, I was an early mover in using open source and embedded systems back in 2000. Here's a lovely picture of me about then. In my first, I guess it was a Motorola, a PowerPC board running with Linux. Forgot her. And my early days very much spent working in the mobile space. I was working Nokia on what they were then calling web tablets. This was about 2000, a couple of years before the iPhone came out. Then helped build a lot of the automotive companies moved towards Linux in their in-car entertainment and entertainment systems, which cross entertainment technology as well. And we worked with Arm a bit on some of the prototyping. And one consistent issue I found all through this. Yeah, excellent. I think that's good. I like to see people say things. Thank you. Always the chips, always the point, right? Especially when you're on the cutting edge of things. You got silicon errata, you're building drivers, things which aren't behaving the way that they're supposed to. The hardware choices you make at the start of the project tend to end up being wrong at the end of the project. And so, a couple of years ago, I was thinking, is there a way to actually do something about this? If you're looking at it, if you've got a suitably large volume of market, got a couple of options. You can build your own chips. And one of the best experiences I've had actually was working with Nokia, because we had a really close working relationship with TI, the Mach 2, Mach 3. We really there was direct feedback. We had engineers on site. I've never had that since, right? That model died probably about 2007, I guess. Other than they don't use the FPGAs, which I'm sure everyone here knows a lot about, which is less investment, but you are going to want to be bought, right? Depending on what you do, right? Doing it really simply, you get a nice cheap Chinese FPGA in the and of course you also got the your supply chain questions as well. I'm sure everyone hit fun supply chain issues in the last 4 years or so. And so that's an interesting thing to get around that. So, what background in open source? Good open source comes to the rescue. And I started digging in on this many years ago now, I guess. And there's been a really interesting long history of open source tools, chip design. It's the big guys don't like to admit that it's there or what it's capable of. But there's been a long history, and some really interesting stuff. The Open Titan guys, they've just done the first commercial, fully open source chip design for security, the security module. Got a lot of groups, and even software going all the way back to the 90s, right? And some newer stuff funded by both EU, US governments. And some sort of interesting Chinese stuff as well. And then there was a really big push at some point on from Google on this, and providing free tape outs for objects. It's an interesting thing that may still continue. And so what we built here was, can we build a modern development environment, something that is comfortable for software guys as much as for hardware guys and girls and others, that allows you to both target an FPGA and actually build an IC in the end, right? So you've got that, because one of the biggest problems with when you're going to build a chip, it's a big decision for management, right? You know, it's, okay, right, we're going to put down 10 mil for the first year. We're hiring the team, paying tools. I mean, the cost per engineer is going to be somewhere around 500k a year, 400k a year, because you're going to pay the license for the software. They can cut all that out. And so we've got kind of like, you know, GitHub-based environments where you can write code, target your FPGA, run it in simulation locally, but then also in the back end, you've got constant tape-out happening that's, you know, working with our foundry partners and our OSAT partners. So you actually are always ready to actually tape out a chip, right? Whenever you're confident in. So that's what I'm going to talk about a little bit today. One of the key things you probably need in all this is some really good debugging with timing information. So there's a nice VS Code environment here, gives you the full information. Actually, can even go like it's got an understanding of the design as well, so you've got that really kind of you can get see transactions and you see stuff at the level that's actually happening and directly related to the code base you're working with, right? So whether that's the current version of this has Verilog and Python support for doing hardware design, and we will be bringing out system Verilog, VHDL, and maybe some of the interesting pipeline C environments that are coming out the open source. Then on the back end, you just plug this into your CI, right? Or you can run it from command line or your VS Code environment, get a build and get your feedback there. And it will also start, and in a later release, we'll actually have all the timing information come back from that, so you can check that you are actually within all your timing constraints. That's a bit hard to see, isn't it? Maybe we should switch the light out. I'm old school 633. Does that go? See that okay?
Yeah.
Excellent, excellent. So the whole idea of the Python side is really just to make the assemblage easier. I mean, you can actually use the Python to write anything that any digital design of any complexity, right? But where we find it really works really nicely is, you know, I've got some components and I'm plugging them together and I want to get something up and running quickly. And so the environment here, this is actually straight from the example code base. I'll give you a link at the end. As you can see, as well as building the IC, it's also generating the software, the IC that we're making, or the target FPGA environment. So we can set up our software generator for plugging in a CPU. This is actually an interesting CPU written entirely by Minerva. It's not, you know, it's a pretty simple, two-stage sort of, but there's a whole world of great open source ICs out there now. Open source RISC-V cores. Stick in our arbiter. We're going to plug in our SPI flash. We're going to have some SRAM in there. And that will also the chip that'll actually generate from SRAM. We'll use the appropriate block RAM, your FPGA. Well, that's some GPIOs or some UART. And a nice I/O bus as well. We're plugging those into, and then we're going to generate the software and generate the design. So that'll give us our tape out with our timing information, or I'll have a look at how it's done on timeout, on the area usage, block design. Well, it'll eventually have power domain design as well. Let's do one How do I press a button?
You press the blank button at the bottom.
Near the play. It's a video, so yeah, I'm not really sure if how to make this play. Oh, play. There's a play button.
Oh, there you go.
No, that did the wrong thing. We can. Oh, that's a video in a PowerPoint. So you just go click play there.
Yeah, I'll do that. Yeah.
Thank you.
Okay. There you go.
So what we're going to show here is actually kind of building the design for there's a built-in simulator here. So this is going to actually show you building your simulated design, running your software on it. So it's just show you what's going on. This is the design we just went over. And here's the a little simple kind of main.c for it. Just go through a few things, say hello in cat language. So you just go run, sim run, build. That was it, building a simulation and running it. And you see there's our main executing there. Exactly the same environment. You've got the same sort of thing that happens for going through an FPGA board. I was going to try and do that live today, but don't find my board in time. It's exactly the same on your FPGA board. And as well as that, you can actually have your kind of system level check, your system level verification in there. So the way that this happens in this framework is actually we know what behaviors we want the chip to exhibit as we're running the test set over it. So if we run SimCheck, what that does is actually measures all the checkpoints and checks that they're covering in the right areas and the right time in the right order. And that's kind of a nice little JSON file that describes that. I think that's the end of that video. So move on. Maybe. I think there was a few slides missing, but never mind. Yes, this is actually the wrong slide there. Never mind. Yeah, I mean, I recommend you come up and play with it. Unfortunately, the URL is supposed to be here, so it's .chipflow.io. The getting started guide. You don't need any particular general hardware to be running it. And in fact, probably in a later version, we'll actually have this running directly in code spaces. So a machine you're doing this from the cafe if you want. And deploying to a board that you connect on at home. Yeah, that's where we're at with this. And it's the whole idea here is just keep moving on. So one of the next stages we're going to be doing here is bringing in analog IP partners, so we can have the equivalent IP your circuits that you're using on your FPGA board. You get the same behavior on the IC side. Be able to do things like DACs and ADCs, and maybe even radio at some point. And yeah, that's where we're going to. So, any questions?
Questions for Rob?
Can you actually write the art scale?
Yeah. Actually, that whole design that you saw running, all the RTL written in Python. And the way that works is you're basically writing Python to generate the RTL. So it's kind of like a programmatic interface. It's quite useful if you're doing like large generative designs as well. I want to have a bunch of these blocks, so I'm very even like this, so this you can on this way, you can write code to generate it all. That works quite well. And it's quite simple as well. Just plug in, IP, umbrella piece, umbrella PHDL IP, and just import that as a block and still use the Python framework to kind of do your assembly and organization.
Good. Any more questions?
This is this question online.
All right. Okay. Let's.
Well done.
Spotted. Let's have a look. Is he?
Hi everyone. Question online from Sunbal. Hopefully I'm going to pronounce this correct. Input.json. Can you please give a few details about what's required, Rob?
Sorry,
Could you repeat the question, Chris?
This is from Sunbal. Input.json. Can you please give a few details about what's required?
Right, okay, that's a really good question. Skip back. Oh, it's on the video, isn't it? So effectively, that's kind of like is meant to be alongside your kind of IP verification, which there were supposed to be some slides here for how you do that in Python. But so in terms of the input.json, it really is what we tend to do is actually kind of, so when you run it, you'll get your generated list of outputs, right? The instrumentation points. So you effectively run your simulation and you'll actually get, this is my behavioral file out of it. And then you can check that and then have that as like a golden check that you've got then when you're in your CI, when you're running your system level checks, you're checking against your golden. So did that answer the question, Sibyl?
Thanks for the answer, Rob. Thanks for the question, Sunbal. Sunbal says, yes, that answers the question. Thank you. There's a further question, Rob. This is from Hossam. What are the supported PDKs? Really good question. So in the current one that's you can go and use today, it's the IHP 130 Silicon Geranium PDK. And the next release will have Global Foundries 130 supported. And then kind of probably next on the roadmap is probably a Global Foundries 55 PDK. And the way that works is actually you don't need to sign an NDA to have access to the PDK because unless you're going to be trying to do some analog and stuff, you'll need to go do that then. If you're just on the digital side, we actually insulate you from the PDK. So you'll get to see you'll get to zoom in so far and actually you won't be able to download your GDS, but you'll be able to know that it's working and what the time is coming out to us for your design. Okay, thanks. Thanks, Rob. There's a further question second question from Hassam. Is there any plan for nodes lower than 130? Yes, like I say, next one's going to be Global Foundries 55. Our target node is where we think the biggest market's going to be here is going to be around the 22 FDX 28 space, and that's the main target for now. We're not currently planning on going lower than that because the problem is really what we're trying to do is have something that's quite low cost to start getting on and actually building chips. So we'll, at these kind of 28 plus, you can do a test tape out for 50, 100K, something like that, which is a lot more tractable than it's only when you start going a bit smaller and it starts jumping up into 500K or $1 million, right, for a test tape out. Did that answer the question? Yeah, Hassam says thanks. Yes, it does answer the question. Thank you. I think we could probably better move on. I'll be used up my time. Oh, spot on. How about that?
So yeah, do feel free later from that. Ask any questions or have a look at it.
Thank you. Next up, Frederick. Be here.
Hello, everybody. This is Frederick speaking.
Thank you. You're going to share your screen, Frederick?
Yes, I'm doing that now. Send requests. Am I sharing?
Not yet.
Oh, screen. Okay, there I go. Okay, you should see my screen now. Yes. Hello, everybody. Good morning. I'm very pleased to be here, well, remotely. My name is Frederick. I'm the CEO of Exhaustive Labs. And I'm speaking to you from Belgium, where we are based. Again, very pleased to be here today. So going to shut down the camera so that you can focus on the slides. Prototyping holds a special place to our heart in our company because, as you can see in the title, we have a very specific focus on providing visibility inside FPGAs. And as you can imagine, FPGA prototyping is part of that visibility for this. And you can't fix what you don't see. Please bear with me. I will explain you why and how we have adopted that positioning on visibility. So I've been a designer. We are in good company. A lot of designers here, whether for ASIC, SoC, or FPGAs, of course. And of course, the success of your design also requires a strong and good EDA industry. And in our company, of course, we think that EDA is essential to maximize productivity and let you innovate. At the very beginning of this event, Fleming has explained that, unfortunately, a lot of the good tools that are on the market today, well, a lot of them cannot be reached by many companies, especially the smallest one. And yes, the view we have is that EDA should be better at maximizing productivity and foster innovation, because not all companies really can afford, can use some of the greatest tools that are around, and have to accommodate for those constraints. And unfortunately, EDA has shifted towards an EDA for the privileged, leaving maybe smaller company having to design their own tools or adopt a different flow or maybe do things on their own. And that's what we think. And additionally, if you have been attentive to the recent development in the EDA industry, I was at the GVCon in the US recently in February. And yes, this was referring to the study that Siemens EDA does every 2 years about verification, and they delivered that result that only 14% of the project come to production first time right. They were speaking both about ASIC chip design and FPGA project, and that statement has been very well summarized by Ed Sperling in Semiconductor Engineering in March. First time silicon success plummets. So not only, unfortunately, a lot of tools are not for everybody, but even though the success is not always there. And that's something we have a concern about, because our vision at Exhaustive Labs is really that a well-working AD industry, a diversified AD industry, maximize productivities, but they should address companies of all scales. And that will enable you as a company to really innovate. So from that vision, just a quick word about what we do and why we speak about that. Well, Exhaustive Labs has been active with first product since 2016, and all our clients use FPGAs. And what we really deliver are what you see on the screen here, that probe, that chassis, and so on. These are tools that are used to extract a lot of data from running FPGAs. We speak about gigabytes or terabytes of data from FPGA running at speed. But this is not really about the product I wanted to speak about today, more about the findings and the conversation we have with our clients, because they all use FPGA, and for one reason. And these are the key findings we have about what they do with it. So let's dig into it. So think that gets confirmed by our clients as well, and we think that's an opinion that hardware, and particularly FPGA hardware, should be more leveraged in the flow. So the reason for that, according to us, is that FPGA is everywhere. There are a lot of existing commercial boards on the market today, and in any case, we think that there is a way to use them. So whether you are designing a product based on FPGA, well, or designing an ASIC or a system on chip, at some point there is a way to use FPGA. Well, obviously, when you design an FPGA product, you have a board at some point. This is the board you design. Maybe it can be extended to do a better work, but okay, you have the FPGA or the FPGAs. If you design an ASIC, of course, there are FPGA prototyping systems everywhere that you use before you go to production. And the two key things that our client report, and we absolutely agree with that, is that FPGA hardware, FPGA boards are an opportunity to do two things. First, run a reasonable number of cycles on your project, on your product being designed. That's key thing. That's what they report, that usually other tools which are essential to it can't match the number of cycles run by an FPGA, because you basically have a real system running at speed. So 1 minute of operation is 1 minute of real operation, whereas you could spend hours with a simulation, just simulate 1 millisecond. So that's an opportunity to see your system run under at speed and during extended cycles. And of course, the other opportunity is to have a realistic environment. And that is very helpful to overcome the limitations or the flaws that you have in models, the models you use in simulation. And the third reason why we think that the flow, the hardware should be more used during the flow, is remark and opinion we have is being the design being too siloed. Sorry about that. So if you have a traditional view on a flow, that would look like this. You start from specification and design to production, and that's a very traditional way of seeing it, unfortunately, and it is being developed by everybody in the market, especially the industries as well. And at some point, well, you start from the specification and you go towards production, and somewhere in parallel, maybe more on the left, more on the right, you have software being designed, and that happens. And traditionally, this is the location where you are going to use simulation. So you have started to design something. You want to check whether it complies, it is compliant with your specification. So you need verification with simulation, UVM, and other methodologies. And you are going to use simulation up to late. And if you are a rich company, you can also afford an emulation. I understand there are many flavors, but let's say it's a way to accelerate simulation. So still model-based and things like that. Okay, that's the place, that's the location of simulation. And FPGA prototyping is traditionally viewed as being used there in a much faster environment, more for validation, and especially very useful when you have started to have a more complete software and you want to run it on a real system, so you need a prototype. And there is a left and there is a right. So implicitly, it gives you the direction. So you start here and you end there. And if you want to do a better job, you sometimes have to shift left. You probably heard about that, meaning that you have to take precaution early in the flow. Good. So here, if I ask to everybody here or anybody here about where is debug, well, probably everybody will have a different answer. And that's the problem with this kind of flow, is that usually we see very clear steps and very clear type of tools being used at those steps. And for instance, debugging. Well, first we have to agree on the definition of debugging, but let's say it's correcting the flaws or correcting problems you encounter, or maybe it's also performance problems. Well, it's a lot of things that you need to fix. And actually, what we hear from our clients is that debug happens everywhere. So there is no one single tool to do debugging, for instance. So it's not FPGA prototyping, especially. It can be something else, but you have to manage it. And so if we have a look about the reality that we're observing at our company, it's more like this. This is the same flow, and each and every of these yellow arrows shows you a real case we've encountered with customers where they have used a FPGA prototype. And you see it's very different from just using them in validation and before production. We have examples of people using that for project planning and technology selection. So it's very early in the flow. We have people who actually design things with FPGA prototypes, and not just for verification, that's redesigning something. And I'm going to detail that. So a radio signal hard to model, that was the case. Some cases, verification can make use of a prototype, of course. For instance, we had a case of a video processing application, and they wanted to check whether the algorithm they had developed was compliant to the spec, and the simulation was too limited. And so they have had to use a prototype, and so on and forth. And so I'd like to go into more details about one or two cases here, not all of them, don't worry. So first, FPGA prototyping used for specifications. That might be an unusual case for many of you, or maybe it is going to be very familiar to you. So that's been a case for a company we are proud to serve as a client, and they design a virtual reality asset. And they were in a situation where they needed to get started with the next generation product. So as you can see, for a consumer product, well, there is a lot of pressure from the market. It's basically the market that defines when you have to get started. And they wanted to get started with something not related to electronics, but a little bit was the mechanical design, what it looks like, and it took time, and it had to start. But they were not sure about whether they needed to make a new electronic platform, a new processing platform or not, which could condition the mechanical design. And so they were facing a choice. Do they keep on using the existing platform, or do they have to make a new one? And the project leader, well, he had a key AXI IPs that he prototyped in a AMD evaluation kit with Vertex UltraScale Plus. And that set of IP subsystem actually matched the target, and they were pretty sure that they could run it at a higher speed and reach better performance with the software. So they needed to verify that. And so they built this in the evaluation kit. They raised the clock frequency, and they executed some software. And so that prototype has enabled them to first demonstrate that the existing, sorry for the typo here, set of IP were fit and for the next generation product and could sustain a higher execution rate. For this, they needed to especially have a look at how the traffic was going on a series cascaded AXI buses. This is what they wanted to verify. And so the prototype in this very case has enabled them to decide, start the mechanical design, and also have some cost savings because they realized they didn't have to make a new platform for this, and in turn go faster to market. And so that FPGA prototype has been instrumental to verifying this because it enabled them really observe the AXI bus structure during extended times. And so that has been key to this decision. Another example has been here. I'm going to go quick into the second example, and then I leave the other ones for later. Using a FPGA prototype for design, that's another example of it. So we are a case of a radio application company. So they have typically a radio system with a analog front end, and everything gets sampled and turned into the digital world. And they needed to design some complex DSP algorithm. And the processing was done in an FPGA, so they had a RF-SoC FPGA. But the problem was they couldn't get an accurate modeling of the signal they were sending to it. So basically, they could make hypotheses, make a model of that, simulate it, but they weren't sure about whether the model was accurately representing the reality. And for the people who are in the radio application, well, you know, there are reflections, there are interferences, there are a lot of things that are hard to model or hard to foresee in full depth. And so they decided to design the algorithm live with a live database. And so they captured the signal in the digital world and started to sample a lot of it. Not only that has built a database of the signal that they could use in some simulations, but they did more with the FPGA prototype. They basically designed the algorithm and tested it on the fly as they were designing it. So they needed to define some DSP parameters and also stages and architecture. Well, they didn't tell me everything, of course, but it was golden for them because statistically, that database was large enough and more complete than models. And so the ability to capture signal in the digital world has enabled them complete the design of the DSP algorithm. So you see, we have seen two cases, first case here and there, where we have an atypical use of the FPGA prototype. And rightfully so, I'd say it has been a good idea for all the two companies. They succeeded in doing that. So for the one who are interested in the other examples, you can just email me. You are going to receive the slides. We have a few success stories. Well, the chance we have had was to encounter all those customers because we provide solution for FPGAs, and so that has been very interesting for us as well. So I'm going to conclude here. So the key findings for us when we work with our customers and clients, especially because they all use FPGA prototyping. So first and foremost, well, FPGA prototyping are great for running under realistic conditions and for speed. So these are the two main technical reasons why you have to use them. And you have to leverage FPGA prototyping for this. You can build your own prototyping board. You can buy a prototyping board. You can use your target product as a prototyping board, but they are everywhere. And so I'm very, it's easy for me to say that because we don't make prototyping boards. So I just tell you, choose the one you like and make the one you like and make sure that it is fit for you. Because as you have seen, it can be leveraged anywhere in the flow. So that's, yes, what I'm saying here. You can use that for many things, from planning to test, debugging, of course, selection of IP, experimentations. So don't stick to debug or validation. Do something else with FPGA prototype. You should use that because as a designer, you have to find solutions. So there are great tools to do a lot of things during the flow. But, and that's the conclusion, reason number one we've heard from our design from our client for not using FPGA prototyping is lack of visibility. So it's very common that we hear, oh, we do simulation only, or we do this only, because with FPGA prototypes, we can run something, but when something goes wrong, we can't see what's going on. Yes, that's a problem for FPGA prototypes. So you have to plan that visibility. You can contact me because we have solutions for capturing gigabytes and a lot of nodes, millions of nodes and so on, but you have to assess what you need and don't just build a prototype. Build the visibility or adopt the visibility or look for the visibility that you get into it. And there are ways to do that. All the customers I've spoken about do that. So plan your visibility resource with your prototype because you can't fix what you don't see. you can't prove, you can't evaluate, or you can't decide about something if you don't observe it. So that's why we advocate for visibility. Well, thank you very much. Are there questions for me?
Hi everyone,
Questions
this
from the
is
room?
Chris again, running the live feed back in Edinburgh. Fleming has a question. Thanks, Frederick. Brilliant, and we need to get you on an SE300. My question, what kind of cost?
What do you mean, or products, I suppose? Because, well, if you decide about equipping your prototype with visibility, that's up to you. We don't get what kind of cost for the type of products we sell are. Well, you start at something like £9,000 for a very advanced system that goes much beyond the usual tools. But okay, that's not quite the point of my presentation. But okay, you can contact me to get a better estimation of all the options we have. Yes, let's say. Any other questions? Seems not.
Any questions from the room?
That's all the questions on the live feed for the moment.
Okay. All right. Well, thank you very much. I've been pleased to come, and you've got my email on the screen, and you will receive the slides. You can contact me anytime if you've got more questions. Thanks.
Okay, good morning, everybody. Going to talk to you a little bit about the kind of things that we do at a company called DSpace, let you know what sort of activities we're doing. And I'm going to be talking to you this morning about hardware-in-the-loop testing, hill testing. This is a type of technology that's used widely across the automotive industry, used in aerospace, used in drives and electric machines. And I'm going to talk about an application today of FPGAs. So rather than talking about how to develop and design and create FPGAs, this is an application on what we use FPGAs for and why we use them, some of the capabilities that they have. Just a quick one about the company. I won't spend too much time on doing that. Who are DSpace? We're a German company. We're established, been around since 1988 now. And what we do is we help people to develop and test the electronic control systems for cars, washing machines, aircraft, helicopters, all sorts of things that are out there. And the Hill technology that we have has become central to the mechanisms that are used for testing electronic control systems. And the idea behind hardware-in-the-loop simulation is you take your electronic controller or your ECU and you trick it into believing that it's actually inside the car or the aircraft or the washing machine. And the way that we do that is by using real-time modeling and also sensor simulation and other technologies. And what it enables you to do is, especially if you don't have a great deal of visibility about what's going on in that electronic control system, to be able to explore its behavior and look at how it's going to perform in the outside world without having to go to the expense or cost or difficulty of perhaps having a real car or a real nuclear power station or a real washing machine. And the way that we do that is we'll run it in real time. We'll see that shortly. But I want you to see where electronic control unit testing or ECU testing sits within the tool chain. And this is the V cycle that you'll often see within companies that develop electronic control systems. Moving from the left-hand side, where we're talking about creating the electronic controller, performing simulation, understanding how the algorithm will work and how to integrate and deploy that algorithm, all the way through to once we've deployed that algorithm, once we've got a real physical ECU, what kind of activities we go through to make sure it does what it's supposed to do. What kind of motivation have we got for doing this? Well, there's lots of applications out there, obviously, that use electronic control systems, and there's lots of challenges. What we're finding, both in the smart grid industry and in the automotive industry, is the functionality of electronic control units is dramatically increasing. The capabilities that they have, especially in the automotive industry, for things like control of electronic vehicles, advanced drive assist systems, traditional control of traditional powertrain activities. The functionality embedded within the control system is dramatically increasing. And what we need to be able to do is to offer to our customers and to our users an ability to be able to test the functionality of the electronic control systems. And the way that we do that, the principle of hardware in the loop simulation, is actually quite straightforward. On the right-hand side of the picture there, you can see one of our hill simulators. And the idea of the hill simulator is it contains several main components. The most important component is a real-time processing unit. It's normally a PC-based or a Linux-based real-time processing unit. And its job is to run a model of the plant, of the thing that the electronic control systems thinks it's controlling. So there you can see that's your controller. In the middle, you've got the motor that it's designed to control. And the job of the hill simulator is to make it think it's connected up to that real system. And it's got a real-time model of the plant running on it so that it can perform closed loop behavior, so that it can explore the closed loop behavior and the electronic control system is expecting. If I push this, I expect to see that come back. And so that's the first main important part of it. And a second important part of it is the ability to be able to do sensor simulation. You see, with many control systems, with many embedded systems, we're familiar with how to respond to sensor outputs, to outputs such as crank angle sensors or temperature sensors or whatever. But what the challenge is at DSpace is the ability to emulate the behavior of those sensors. And that's what we've done over a period of years. We've developed technology to emulate the behavior of those sensors so that we can make the ECU think it's connected to a real engine or a real temperature gauge or a real strain gauge or whatever. And that's what DSpace essentially brings to the party inside these hardware in the loop simulators. And there's various other components and various other bits and pieces inside the hill simulator. But the most important ones are the ability to be able to run a mathematical model of the plant in real time so that we can see what the response to the actuation signals from the controller is, and the ability to be able to emulate the sensors so that we can have an informed point of view so that the ECU can think, yeah, I am connected up to a real engine or helicopter or car. And traditionally, when we've been modeling in the automotive industry, for example, a big application is engine control. What we've been able to do is to build mathematical models of engines and to be able to run those models on processors, be able to run those models on something like real-time Linux. And the way that we do that is we'll model them in a tool such as Simulink, and Simulink or other tools such as Demola or Adams, they have the ability to not only run simulations PC-based, but also to automatically generate C code. That C code can be run in real time, and that's what facilitates and allows us to perform the hill simulation. But the big challenge that we've had, certainly in the last few years, and certainly as systems are changing in the automotive industry, is that these processor-based models don't run fast enough. So what are we going to do? We want to build a real-time simulator that's capable of representing the behavior of a system. And in the past, these mechanical systems, these engines, they were quite slow. So it was quite straightforward to be able to do that, to take Simulink models, to generate the C code and run them. Now we're talking about high-speed electric motors, or we're talking about much faster behaving systems, the dynamics of which we're not able to run them with execution times of maybe around about 1 millisecond, because the frequency, the behavior of the electric motors is such that we have to run these models faster. We have to start running them down at the microsecond level. We have to start running them down at the nanosecond level. And how are we going to do that? And that's why we turned to the FPGA technology, because obviously the main advantage of FPGA, not the main, but one of the advantages of FPGA, it's its ability to be able to run things in extremely high speeds. And so what we had to do is develop technology that enables us to take these models and run them in real time, not on processors, but on FPGAs. And there are certain challenges that we've got in terms of doing that. And so that's what we start to look at. And one of the first things that we have to look at, certainly when you're emulating or simulating the behavior of an electric motor, is how the controller works and how we're going to use that controller, or how we're going to explore the behavior of that controller. Now, one of the challenges that our customers have got is that quite often they don't have access to the controller itself. They don't have the visibility. Quite often in the electric drives industry, I will go to an OEM, I as an OEM will go to a tier one supplier and ask for a controller, and they will give me that controller, but they're reluctant to let me know how it's put together, what components are, how those components interact with one another. And quite often, all I will know about this controller is if I put a certain current through a certain pin on this controller, then it will control that current, for example. But I don't know internally within the controller how that particular circuitry works. And usually I'm discouraged or even obliged to not be able to explore the behavior within that controller. So at DSpace, our customers will come to us and say, here's my controller. I need you to trick it into thinking it's in the system. And at the moment, the only way of doing that is at power level. I'll physically have to put 20 or 30 amps through the controller. And that's a challenge to us when we're building a hill simulator. What we'd rather do is what we call signal level simulation. So we have the power level, but what we'd rather do is perform what's called signal level simulation. And at signal level simulation, what I'm effectively doing is bypassing the power circuitry of the electronic control system and feeding in signals at the signal level to allow it to think it's connected up to this electric motor. And that's a challenge for us. And that's a challenge that we've used FPGAs to enable us to perform. So we've got these well-established processes within the automotive and the aerospace industry that allows customers to generate C code, but it's not fast enough. So one of the approaches that we used fairly early on was technology that allowed us to translate those Simulink models not into C code, but actually into something that could run on an FPGA, basically VHDL. And we looked at the Xilinx tools, and in particular, we looked at the Xilinx Vivado toolchain. And what we were able to do is to use the Xilinx Vivado toolchain to take pre-existing models, pre-existing Simulink models, and be able to translate those into a domain which wouldn't generate C code, but would generate VHDL. These models, which we call our AESIN models, our automotive simulation models, are off-the-shelf parameterizable models of standard components within the vehicle. So the things like, for example, engine models and drivetrain models and vehicle dynamic models. And what we did was we took those aspects of the vehicle that needed to be run at a higher speed to provide the system behavior that we wanted to. And we translated those into the Xilinx system generator tool. And what we've done is we've provided off-the-shelf electric component libraries to be used to complement the capabilities that we've got in more conventional modeling systems. So we have a set of models that will model conventional behavior, mechanical behavior in engines, drivetrain, vehicle dynamics, those types of aspects that can be handled at the processor level. But we've also complemented them with a set of off-the-shelf models which deal with the electric side of things and which can cater for the fact that we need to be able to model things like, for example, brushless DC motors, permanent magnet systems, inverters. And these models run as FPGA components. They're effectively parameterizable IP cores that will run on the DSpace systems. They'll run side by side with the conventional processor capabilities, and they'll provide us with an ability to be able to perform simulation. Okay, and there's some of the specific capabilities that we have within those. Go through the, okay. I won't go through the basis of it because I think, given the time that we've got, we want to do a little bit of a catch-up. But here you can see the general approach that DSpace have. We produce mathematical models in Simulink, representations of the dynamic behavior of the plant controller that we've got. And then we can either automatically generate code and run them on a conventional processor-based approach, or we'll perform translations to these models to put them in a format at which they can be downloaded onto the FPGA. Okay, at that point I'll stop because I know we want to catch up. But I just wanted to provide you there with a quick overview of the type of technology that we do at DSpace. Thank you very much. Any questions? Yes.
Your model is purely theoretical, or do you have like actual data in the web systems?
They're not, well, it depends what you mean by purely theoretical. A lot of the content of the model is data. So we'll use a lot of lookup tables, and we'll allow the user to be able to parameterize those models so they're specific to their particular circumstances. And that's quite key, really. The other thing that you've got to bear in mind with the models is quite often people will ask us about how accurate these models are compared to the real physical world. The activity that we're involved in hill testing is you're not really interested in whether or not, for example, when they apply the brakes, that vehicle stops within 200 meters or 150 meters. You're more interested in the behavior of the ECU if the brakes fail, or the behavior of the ECU if it starts to slip. And so hill testing is about exploring the various behaviors and exploring the various modes that the electronic control unit has, rather than trying to check its actual performance, as it were. So it's a good question about accuracy or theoretical side of things. The answer is really, as long as that system exercises the ECU in the way that it would in the real world, then that's the most important thing.
Any more questions from the room? The question here.
Yes.
Basically, I want to ask about your modeling. Do you take into account things like temperature?
Yes. So the behavior of them, what you've got to remember is we're modeling the real physical world. And if temperature is important, then yes, we will do. So for example, if the ECU is going to respond to temperature and temperature is a factor, then yes, because the model is effectively just a state space system. And so whatever the ECU is concerned about, we would model. So for example, if we're modeling something like a diesel engine, then yes, temperature can be very important.
Is do you get used a lot for sort of ISO 26262?
Definitely, yes.
Cases? Yeah.
Yeah, because it's a demand often of ISO 26262 that you perform hill testing.
And do you have like a mini oven that you put the ECU in?
Oh, there's all that kind of stuff. Yes, I mean what we'll have is customer requirements in terms of putting it inside a chamber, temperature requirements, shaking requirements. And some ECUs are much more challenging to work with. So, for example, we're working with a motorcycle company, and the braking systems in a motorcycle company, the inertial capability is often built into the ECU. So we have that challenge there where they're saying, here's the ECU, we want you to emulate the behavior of the sensors, but they're all packed into this control unit.
Yeah.
And we sometimes have to build systems where we swing this thing around and make it, or tilt it, or move it. So our job is to basically say, here's the ECU, it's going to go in a motorcycle or a helicopter. How can we make it think it does that? And to what extent? So how does the ECU know what acceleration is? Well, within the ECU, so the actual chip of the ECU, there's a voltage, but that voltage comes from an inertial sensor. Do we shape the thing around to do the inertial sensor, or do we bypass that inertial sensor and directly inject it? And it's the same, for example, with cameras. We do the same kind of capability with cameras, either physically pointing the camera at a screen or digitally implanting a signal from an HDMI feed into the camera.
Yeah.
Okay, all right, thank you very much.
Oh, hold the phone. We've got a question online. This is from Sunbal. Does DSpace provide all models, or do you provide hardware and the models are built by third parties?
Both. We provide our own parameterizable models, particularly in the automotive area, but we'll also work with customers that provide their own models. And they can also provide their own models in terms of C code, Simulink models that is going to get translated to C code, or their own VHDL, or their own Simulink models, which are designed to generate a VHDL code. So the MathWorks, for example, with their Simulink tool, they have a VHDL code generator. So we can work with all of those. But in the main, what we've done is provided that technology that allows us to be able to run processor-based models and FPGA-based models together so that you can model all aspects of the systems, some which more appropriately are modeled in C, others which are more appropriately modeled with high-speed VHDL.
Okay, thanks for that question, Sunbal.
Thank you.
Thank you very much.
Hello, everybody. I'm Taner Dostal, the founder and CEO of VTech. And as we are a startup, you would not have heard what we do. So here it is. So we are developing UltraEdge, which is a real-time power and control system optimization. So I'll just talk a little bit about how we do that, what that means, and then go, of course, into what we did with the FPGA, and that allowed us to develop this solution in a very short time, in a very limited budget. So at a high level, this is all about the paradigm shift where we move things from cloud, local edge, to even down to the micro level. So people talk about the edge solutions, but what they really mean is the sensor data is just as it was before. Instead of sending all the sensor data to the cloud, let's do something with it at the edge. What we're saying with the UltraEdge is let's actually start looking at the circuit level information that is not really coming from the sensors, but it's within the control loop. Can we actually get inside the control loop and look at an information that's not coming from the sensors? It's already part of our control. And that's what we developed. And this is why we called it UltraEdge, just to emphasize that it's not an edge solution. It's something slightly different because it's inside the controller. A typical microcontroller would be just essentially looking at the error signal and correcting it. So what we are able to do is provide this, let's call it supplementary function, that will predict, detect, and correct the system response when it's needed. So typically this would be during the transient times, during the nonlinear response, during the extreme cases. That's where we would just detect it and act upon it to correct the system response. Now we're able to do that within 1/10 of a millisecond. That's 100 microseconds, and that is essentially what we thought we would want to do to be able to really achieve what we call real time. I realize when people refer to real time, they just say, well, we did the best we can with latency. What we mean by real time is that you need to be able to, if you're acting within the control loop, you need to make sure the whole of the system dynamics is also essentially not impacted in a way that you don't want. So that is, for us, the real time. So this is basically what we set out to do. And of course, as a small company, we are a semiconductor company, and this requires a lot of effort, funding. So it was sort of natural to first having to do this in a FPGA for verification. Now, before we get to that, maybe just look at all paradigm versus what we did. Now, when I call it old paradigm, this is really the IoT approach. So it's really maybe still the current solution for many people, and for good reasons. It works. You can have multiple sensors. You can keep adding more sensors. And in fact, all the sensors from the data, you don't have to send to the cloud anymore. The edge devices can do a lot of the processing, reducing the data. And this is really something that works. The problem, or at least the challenge with this, is you still have to be collecting all that data. And you still, if you want to do some kind of prediction, some training data is required, historical training data, for you to develop models. What we did is instead get inside the control loop, as we said, through the microcontroller. So we are acting upon the data that's really about the system response. So we do not require historical data, because we are actually everything that we need, we obtain during the start of the system. It's pretty much like an auto-tune calibration is all we need to be able to get our model together to act. And so this has been a big breakthrough, that you don't have to be building these massive models. The second one, of course, is as we have that data, you can still send that data to the cloud for further analysis. But as we are obtaining this data within the control loop, we are able to provide a correction. So, and this is really the one of the few systems that does that real-time system response correction as it happens. And so a lot of times we basically correct the error, and what we're reporting is if we hadn't corrected, what would be the error, which is a lot better than actually sensors actually seeing the error. So what was the approach? What we did is a typical motor controller. You would have the models of the motors, sensor models, and all of that we build in HDL, basically, so that we would be ready for the silicon, of course. And we build this on an ARM Corestone 300 platform. And the reason is we looked at the capabilities, and it seemed like it's offering everything we needed. So for no other reason. And of course, we are an ARM flexible access program, so we had access to it. And though you add those two together, we basically initially put this together and simulate it. But with the simulation, you can, of course, have a process so far. But the simulation results is essentially gets you to verify that the concept and approach is okay. And here, I'll show you how that worked for us in the simulations. So if you look at a torque transient, this is a graph where it shows inner current loops. The y-axis is the torque current, the x-axis is the direct current of the motor control. And so if you change the speed and torque, you have these clusters of data, which is the steady state points. And when we talk about the transient, it's really going from these steady state conditions, what kind of path the controller takes. Simple enough. And if you can basically play with the configuration parameter, and for a slightly non-optimum controller, you would see that your motor will have to build the magnetic flux before it applies the torque. And that causes that blue path between the transient state. So when you do that, the current looks like at the top right, where you make a very harsh transient, your motor can stall, and you would have very much peak currents. And of course, EMF as well. There is us. Exactly. So what we said, well, we can correct it in real time in the loop. And yes, so we apply our alter edge. What we're able to do is essentially, instead of those blue paths, we make the corrections. And so the transient is what we wanted. Now, of course, this is all simulation. So what do we then go to the customer with is that actually we want to put the motor and show this fantastic results. And that was only possible with an FPGA. again, for us, it was just a matter of taking that previous HDL code, having Xilinx Vivado compiler to generate the code that we want. And it looks very similar, except instead of the motor models and the sensors, we just build the board. We build the driver, we built the sensor boards, we had a big motor in the lab, and then the box was the FPGA. So here, that transition from the model you can see from the FPGA is fairly straightforward. All the models are compatible. So, and I'd like to think that it was that easy. We just added a few people and bought the prototyping board, and we got the results. It was pretty close, actually. So it's not that far off in terms of the reality. Here, we're talking about the driver board we built, that's on the right. So this is essentially the model of a typical transform. The top boxes are what you would normally see in a motor controller. I guess you can see Ultra Edge is just coming in real time and correcting the response. So we build that into the system. The second thing is, this is, again, just showing that there is some hardware building the boards that you have to do, interfaces, but put it in perspective from a semiconductor to build this, it would be at least a year. But here we're talking about months to put this board together. So as we did that, we got ourselves a system, and I'll go directly to the results. So instead of me showing those graphs and say, I simulated this, this is now an actual motor. And I'll show you the details of it again. Running, and this is our GUI, looking at the motor and showing during the torque transients how we can correct it. So if you look at it again, the top is the speeder, and you see the torque transient without the correction, up and down. And the second is you have the same torque transient, but now with the real-time correction. And you can see how the error is reduced, the path is corrected. And for me, that is the real time. You have this whole concept. That graph that I showed you was good, but I would have a ton of questions. Instead, when we started showing the actual motor running with the torques, where people can actually change this, and we can do this demo in the motor, that becomes a whole new perspective. Then you can see that we are actually really acting upon real time, and our models are much more effective than what we're seeing typically. And in that video, basically what we had shown, just to repeat that, is if you look at a constant speed and then you're looking at a torque transient, you would have a error, speed error. It's a linear system, it has to build a error to respond to it. So that's typical. And what we're doing with the Ultra Edge is, by predicting and correcting that, we are eliminating that error from happening. But we have the information that if we hadn't made the correction, this would be the type of error that you would get. So two things that suddenly becomes available to you. One is we did correct the speed error. You can have many applications by regulation, reducing regulation margin, by reducing peak currents. But we also have this information. As the system ages, we can tell the difference between a healthy motor and an unhealthy motor based on our response, what we had to correct. So we suddenly have an information that is just not available otherwise. And since we're correcting it, it's not available at the output of the sensors either. So that suddenly becomes another interesting application of this. And that's us. With the FPGA, essentially, I'm just going to talk a little bit about in terms of the results, as you've seen in the video, what that amounts to is we have certain torque transients. And if I were to, in this case, collect the sensor data all the time and see if I could just make sense of the torque transient, this is what it would look like. So I would have to collect a million data points every second. Whether I do it in the edge, in the cloud, that's the data that would be available, because that's the amount of data that I'm actually handling. And it would look like this. And of course, I can do principal component analysis and do a vectorization. And it becomes obvious. I can, of course, find where the torques or transients are and see what the events were. But remember, this is after the fact. So I had collected all the millions of data points, sent it to the cloud, and said that there's these torque transients. At the end, I would say, yes, there was 6 torque transients, but it would be already too late. It would have happened. And all of that data essentially is the same thing that's happening. And instead of having those millions of data points, the world looks like that to us. We basically detect 6 events. We predict and respond in each cases. And if you want, we have captured these 6 data points, and we can send the information about that. And if you combine it with a known model of the motor, because it's just rest of the time it's just behaving as it should, as a linear system, all you need is this limited data sets to actually accurately recreate exactly what the motor did, instead of going to the millions of data, having to transmit that. So that itself is, we found that as important as our ability to do real-time data control. And this, as you can imagine, was the time frame for development. Us being able to do it in a real motor was made possible by, of course, doing an FPGA. I should emphasize, FPGA is one aspect of it. We use EDA tools as one of the sponsors of this synopsis. We are part of Silicon Catalyst program. We have access to various EDA tools and the Foundry. And all of that combined essentially allowed us to turn this solution, prove it in FPGA. And last month, we taped out our silicon with all of these HDL code, the C code, the Python models, all of that available that we've already verified in FPGA is now going to be, when it comes back, in silicon available. And that development is for us the key value for us to not only be able to do the validation before the silicon, but to explore a bit more of what the technology can do in the lab environment. And in this case, we were able to evaluate themselves. So the rest of it, there is a ton of things. There's details. I intentionally didn't go into all of our compilation tools and the software environment. That would be definitely longer than half an hour, but there is lots of details, of course. But please feel free to ask. I think I'll develop essentially first tested in FPGA, now available in silicon. It's all about an IP that could be a companion for a microcontroller. It can be a simple microcontroller by itself as microcontroller to actually do the motor control. But as importantly, it's a software and what we call the dynamic digital shadow that provides access to real-time data already extracted that provides detect significant events in real time of a motor control, power inverter, some of the power electronics. With that, I don't know how I'm doing was I too fast or no?
You're doing good.
All right. Thank you very much.
So, questions from the floor. Okay.
Hi. Do you provide the IP or you use the Ethos 55 to run your model?
We actually develop our own IP. The Ethos is for accelerator. We use, in this case, Ethos, but that's just an accelerator. So how is that? Why do you ask about it? Same within the same sentence as IP. Because for me, U55 is just the core that I run.
What you provide your customer? Is it an IP that runs model, or is a model that runs on some accelerator or any other platform?
Okay. Two things. If you don't buy our companion IC, which would be coming from silicon, that's easy. If you don't do that, you would have a custom digital in the form of HDL, C++ code that's running the pre-filtering, post-filtering data processing aspects, and a Python code and TensorFlow-like library that has the models that could run on an accelerator. So all that combined, and of course, those are just deliverables. And overall concept of the supplementary controller is the technology and the IP. And really the approach is where we have the patent, for example. But our deliverables are specifically the firmware code and the software code.
They move on the floor. Questions? Chris, any questions online, Chris? Seems not. Okay, thank you very much again. One more talk or two more talks? Yeah. Okay. So could I ask James to the...
Thank you. Okay, so good afternoon, everyone. James, I work at ETAS. For those of you who don't know, ETAS is a subsidiary of Bosch. So where Bosch build a lot of electronic control units that go into cars, we develop a lot of the development and test tools that help around that. So we sell to Bosch, we sell to Bosch's customers, and even to their competitors as well. So one of the things that Bosch is very active in is ADAS systems, so advanced driver assistance systems. And we have helped them here with some projects. So I'm going to talk about the role of deterministic recompute in ADAS development and testing, with reference to how FPGA prototyping has helped with that. So the first thing to say, when you're looking at an advanced driver assistance system, is you're interested in basically collision avoidance. We've got some sort of perception system, the cars or the vehicles moving about, and the perception system has the goal of stopping the vehicle crashing into things around it. And in the good old days, that when you took a car for a test drive, you booked it out, drove it around a bit, came back, did anything fall off, then we're probably good to go. But these days we want to drive around, we've got camera systems in the car, we've got LiDAR and radar, various you're driving down the M1 and really nothing happens. It's the same environment. And the basic problem is that finding those rare events where you're interested in how the ADAS system's going to react, they're very, very rare. You're 1 in a million hours of driving. So it's basically impossible to plan a test drive where you can expose your system to the relevant kind of events. And so therefore, as we've heard in some of the other presentations, what we're interested in doing is capturing those bits of interesting data and having them available to play back to our system under test. And that leads to an interesting thing. So in the automotive industry, just like every other industry, people are wanting to do things faster. So we end up with this validation cycle where you build a system, you put it into a vehicle under test, you drive it about, record what happens. You want to look, say, did it do the right thing, change the system and repeat the cycle. Of course, now we've got the ability to do that virtually. So we can take our test drive data and we can play that back to the ADAS system in the cloud, could be in a health system, could be on a desktop system, whatever it is. The point is there's lots of different computing environments where the same data is being processed. And that's all well and good. We want to make things cheaper, we want to make things faster, but the key thing with collision avoidance is you want it to be predictable, you want it to be repeatable. Nobody's going to trust the system if it behaves differently when seeing the same data under a different compute platform. So our colleagues at Bosch, they developed the module on the right. This is a multi-purpose camera module designed to go into vehicles. And I believe it's just actually been launched in its first production environment. So it's going to be driving around on the streets really soon now. So this is FPGA based. And the FPGA is important because it's a multi-purpose camera. It's designed to do different things in different situations. So you might have, within the same OEM manufacturer, they might have different vehicle variants. Some of them are built with fairly simple assistance systems. Some of them could be, going much higher spec. You could have ideas about repurposing the vehicle. You might have something that's a pool car by day, but at the weekends, it's autonomously patrolling a facility, as a video surveillance vehicle. But the key thing here is that if you've worked in embedded systems for any amount of time, you realize that this virtual validation cycle involves a hardware loop and a software loop. And embedded systems are notorious. When you bring the hardware and the software together, it never quite behaves as you expect. And that was indeed the case in the long development of this multi-purpose camera. So this module could be doing something like road sign recognition and sending a complete signal. So it's doing all the processing on board in one unit and sending a result out to another vehicle system to adjust the road speed. It could be looking at video data coming in, doing some pre-processing and sending those pre-processed results out to a central compute unit that's then doing taking the decisions of controlling all the vehicle systems, the steering, the braking, the propulsion, as to how you do collision avoidance. Or it could be acting just as a camera and just sending raw video data out to be processed somewhere else. But the idea is that when you've got ADAS systems in the car, you're working with embedded at the limit. You've got a lot of data. It's very high bandwidth, very high data speeds. You've got to move that around efficiently. As I say, we want reproducible behavior in the system. It's got to work the same way every time. And because it's going on the road and we're all entrusting our lives to it, it's got to support safety requirements. So not just things like ISO 26262 and how you've developed and tested your system, but also increasingly the regulation that's coming from government bodies around the world that's going to end up being different in different countries. So you have to be sure that you can prove your system is always conforming to the necessary regulation. And as things change, I mean, everybody's talking about software-defined vehicles, and what does that really mean? Well, you might want to update the software in your system and prove that those updates still work the way that everybody expects. So what this is leading to is that as the number of hardware compute platforms involved in developing and maintaining and validating these systems increases, we start to look at domain-specific middleware. So we're having an ADAS-specific middleware that helps to make sure that the ADAS is always doing its job. So have a look at an example. It's probably easier to see. So what we've got here is the camera driving down a city street, and there's 100 frames of video data. And what the camera is doing here, it's detecting objects that it can see. And on the side, we've got a graph showing the number of objects that have been detected in each frame of the video. And that's well and good. So now we're taking that same 100 frames of video data and replaying it back in the lab. And this time it's running on a Linux system with the ROS operating system. And you can see with the purple line, again, it's detecting objects in the frame, but you can see it's not always detecting the same number of objects. So, you know, if you're that cyclist in the picture there, that might be quite a concerning situation, because now we want to be sure that in both systems, the collision avoidance decisions that are being made have got to be consistent, whether it's running on a lab-based system or whether it's running on the embedded system in the vehicle. So this is the kind of problem that the project guys were seeing, and came to ETAS and said, right, you guys are experts in real-time and embedded. What can you do to help? So we looked at this and said that, okay, in most embedded systems, there's a fairly simple, well-known model. You've got a data producer, in this case, a camera, and it's providing data to various consumer processes who are doing something with it. And the number of consumers and the rate they're consuming the data can change. But generally what happens is there's a lot of data that's being copied around in the system. And there are interrupts going on all the time. You know, there's different buses, the different peripherals working. You've got to cope with temperature variations. You've got to cope with all the things that we know and love about working in constrained embedded systems. And it's this data copying process that was leading to this problem. So specifically, the image data is being chunked up. You've got different consumers that are working on detecting objects in different chunks of the image. And if you don't manage the copying of the data into the buffers and making sure everything's synchronized, then you get this problem that in the same frame, different compute platforms don't see the same result. So what we've looked at doing is coming up with a new approach where you manage the data copying much more strictly and basically have a zero copy approach. And this again is where prototyping systems come into play, because whatever embedded compute platform you've chosen for your system, there's going to be trade-offs in the amount of memory available, the peripheral sets you've got available, how the memory can be shared between processors, how fast it is to access, you know, what mechanisms you've got for doing mutual exclusion around access to data buffers and that kind of thing. So by analysing the data path in the system and using an FPGA to prototype that, the team can look at it and say, okay, we can come up with a nice solution where the data doesn't move around so much, so we don't have so much risk of the consumers seeing the wrong data at different times, or not being able to copy the data before it's replaced and that kind of thing. And we can come up with a much more reliable system that allows the ADAS perception algorithm to always see the same data and make the same decisions. So again, the value is in using the prototyping to make those kind of trade-offs, look at the customer requirements, because everybody's saying, you know, once you've got it working, make it smaller, make it cooler, make it cheaper. So you've got to keep coming back and validating these every time with every new project, every new change to the algorithm, what it's doing. There's just this constant approach to managing the problems around this. So if we go back now and look at the same data, so again, same video scene, running in the inside the vehicle in the FPGA camera system, detecting the objects again. And I must admit, I haven't actually compared the two to see if it is actually detecting the same objects in the two runs, but I assume it is. And now again, taking that data and playing it back on a Linux system, and this time you'll see the purple line exactly matches the blue line. So the results are the same. We're getting this deterministic recompute of the video data. So now we can be saying to the team building the anti-collision algorithms, you can go ahead and develop whatever feature you're doing, whether it's retraining your model on new data, or you're trying to optimize whatever goes on. But we can be confident, if we're using our deterministic middleware, that we can replay that on any of our test systems, whether it's in a prototyping environment, if it's in a hill environment, or a desktop, or a cloud-based environment, that anti-collision system is going to get the same results, behave the same way, and we can trust its behavior when we're developing this to, obviously the end goal is to be driving around on the street. So we can say, right, what we're seeing in the car is equivalent to what we're doing in the laboratory. And why is that important, having the vehicle environment the same as the validation environment? Well, again, people have talked about left shifting bug detection, and that's exactly what we're trying to do here. We're trying to find situations where the collision avoidance isn't behaving optimally. I used to say about, you're driving around and suddenly an ostrich runs in front of the road. And I gave a version of this talk in Essex, and a guy had been on a test drive around Billericay and found a peacock in the road. So it's like the only way is Essex. So what we're looking for is finding things that the algorithm hasn't seen before, capturing that data, adding it to the training database, building a new version of the algorithm, and being able to say, right, let's do this. And not just show that it works, but also having forensic regression and saying, what versions of this have we got in the field? What do we need to update? How do we need to plan rolling this out to the systems we've looked at before? The next thing is just in general function development. So people now, everybody's moving to a CI/CD tool chain. Everybody wants to have everything script and working as fast and reliably as possible. And now that we've got a deterministic way of working with the data on different compute environments, then we can easily do that. So we can build up, whether it's cloud-based, multi-parallel test systems, and you get the same results as the guy who's sitting there with the EVB on his desk, working, at the absolute edge of the latest reported development. And then finally, the other thing is stress testing. We've got to prove that this works under different circumstances. We've already seen that you have to collect an enormous amount of data to do that. But with the middleware, if it's designed correctly, we can actually use the middleware to start varying the processing conditions and start to say, can we cope with X% more interrupt latency? Can we cope with things slowing down because of temperature rises or whatever? So you can start to use a prototyping system to bring out those, embedded level stress effects in the system. So when you're planning to roll out an update over the air to vehicles in the field, you've got a good way of showing the certifying body that you've been able to do that. So in the middleware, there's a bunch of stochastic mechanisms that you can use to do that kind of testing without having to worry about how do you plan test drives to capture suitable scenarios. Okay, so bringing it all together then, when we're looking at this in a typical project environment, so we've got the developers, and they're building their vehicle system, whether it's on a physical hardware, it could be a ARM64, where that's a hard or a soft core running a POSIX operating system in some kind of prototyping environment, or on an actual board on a PCB, or it could be a Linux system running on a Windows PC. But the idea is the same. You're building your system, and you want to do some kind of test run, and you see a problem. And here, the kind of problem we're seeing is the collision avoidance is suboptimal. We're seeing a cloud of peacock feathers drifting around in the air. So the idea then is we can then look at the data that's been recorded, snip out the bit that's of interest, and use that to find the actual window when the problem occurred. We can then use that data to now debug and fix the problem. So basically use it to retrain the perception system and then run that back on all of the different validation platforms that we have, whether, all through the whole system to debug and fix the actual functional code. And then we can validate that by varying the parameters slightly to make sure that you get acceptable performance of the collision avoidance before rolling that out into the field. So again, we're validating that fix and trying to show that because we've got this deterministic, trustworthy recompute facility, we can be sure that the perception algorithm, however it's been trained, will always make the same kind of decisions when it sees that data. So there's a web link at the bottom there if you'd like to find out more or come and have a chat with me. Be more than happy to discuss this. But hope that's given a flavour of why we've been involved in building this system. FPGA prototyping has been a key part of that, along with the embedded software knowledge that our team up in York brings to the equation. So thanks very much for your time. Anybody get any questions? No? Okay. No?
Okay. So good afternoon. I'm Xavier Mattes. I am field application engineer at Synopsys, and I'm working on supporting the hardware-assisted verification solutions that we offer at Synopsys, and we are very glad to sponsor this event today. Okay, let's start. So today, the title of this presentation is going to be EP-ready hardware-assisted verification platforms. By EP, the EP stands for both emulation and prototyping. So we're going to see how a single hardware can allow you to work in various use models and use multiple use cases on a common hardware. And that's really what this EP-ready solution is all about. Let's move on with the mandatory disclosure. Okay, these are forward-looking statements, so as of today. Okay, today we live in a very exciting environment. We call it the era of pervasive intelligence. So we have an amazingly amount of software and silicon content. So this is really increasing, and this happens in system products. So what we see, for instance, is in the field of autonomy, software-defined systems are reshaping the industry. So one example is the car, which we've just talked about. So we're getting to things which are really complex, which we couldn't have imagined maybe a few years ago. And now people need to validate the equivalent of thousands of kilometers driven by a car. So you need some ways to fasten your validation. Finally, we see also the driving demand for massive compute, okay, like AI, and it's happening both at the edge and in the data centers. Okay. What we see also is compounding complexities. So for instance, if we look at the software, so we got a measure that was made by AWS showing that from the years 2000 to 2030, the amount of lines of software code is going to be multiplied by 6,000. Okay, so it's tremendous. It's tremendous amount of software content that is brought into the new systems. Also, if we look at the hardware side, we see that we have a variety of designs that go from very complex, like for instance, a telephone, some automotive applications, but which can really get to a very high complexity. For instance, when we look at NVIDIA GPUs. So we need to be able to scale from things which are kind of small to something which are really gigantic in terms of ASIC gates. What we see also is how fast the interfaces are changing. Okay, and Synopsys is a major provider of IPs. So for instance, we have USB, Ethernet, MIPs, and so on. So we provide interfaces as IP. And so what we see, for instance, is the bandwidth for the memories, which is going through the blue line. So let me see if I find the pointer. I'm not sure. Okay. Anyway, so the blue line, so that's the bandwidth of the memory. And what we see is that if you look at the hardware, the hardware flops, okay, so the number of operations that needs to be performed, you see that this curve is increasing more rapidly than the actual bandwidth. That leads to making clever choices in terms of architecture. Okay, we're not even mentioning all the large language models and the AI, where we see that the transfer size is rising up like hell. Okay, so it's no longer following the Moore's law. Okay, and we see really big complexity. Okay, so we said that it was important as well to discuss the architecture, because you want to make a good trade-off between power, performance. So you need to explore how you want your compute to be done. For instance, is it going to be a CPU or a GPU? You want to be very careful with your interconnect, so you get the best bandwidth out of your interconnect, and you will be able to access your data in order to process them. And then also, you need to carefully choose your chiplet interfaces. Okay, we talked about different protocols in this land. So all this complexity doesn't sum up. Actually, it multiplies. Okay, so that's what is making hardware-assisted verification so mandatory. It's because you need to verify through quadrillions of cycles because the complexity is huge. Okay, fortunately enough, verification happens in phases. Okay, so you would start at IP level or core-centric kind of verification and start to do subsystems, software, hardware co-validation. That can be done using your simulator. For instance, at Synopsys, we have VCS simulator. So that's doable as far as the complexity is not too big. Then on the other side of the scope, okay, so we are not able to read. So we have silicon at speed. So this is the purple arrow. So at the end of your project, you want to validate your software directly on your real silicon. Okay, but the problem is how to bridge the gap between simulation and real speed kind of verification, and that's where HAV, hardware-assisted verification, comes into the picture. So for instance, if we look at emulation, we see that we're able to exercise 5 to 6 trillion cycles. So that's for emulation. And of course, when you go to prototyping, the frequency is a lot higher, and you're able to run 2 to 3 petacycles doing prototyping. Okay, so you need here, what we see is that we need to be able to scale, okay, to go from an IP up to a full chiplet or a full system. So scalability is a must, and we're going to see how we can do that. Okay, so we discussed about how the complexity, hardware complexity, software interfaces, architecture. What we bring is those HEV platforms, EP-ready platforms. So to address those challenges, we bring extremely fast platforms. Okay, so that's about performance, scalability from small designs to very large designs, configurability. Let's make sure that whatever is your use model, we're able to configure it in order to apply this use model to our HAV platform, and the total cost of ownership. And this is really where Synopsys has a great value, is because we are able to provide for a single hardware configuration, we're able to provide multiple use cases, either prototyping or emulation. Okay, so these are the use case that we have at Synopsys. So here, this is our tool called Virtualizer. So you build a virtual model, basically C models that you assemble together. So it's extremely fast and not necessarily cycle accurate. And what you can do is to do hybrid prototyping, doing both virtualizer for the virtual parts and put some hardware into the HEV product. So that's one way of working. Then we have everything which is related to simulation, like RTL, early RTL verification. And you can speed up this simulation, co-simulating with the hardware. Okay, and then we have RTL regressions. So all of our ecosystem is able to interact with the hardware-assisted verification solutions that we have. Continuing, then we have ZeBu Empower. So ZeBu Empower is typically our solution to do power and performance analysis, and it runs onto the hardware and is able to extract waveforms in order to compute your power. We have everything which is related to interfaces, so HAPS protocol interfaces, card, speed adapters, transactors, and so on. And finally, if you want to work at real speed, okay, and do some compliance or certification of your protocol, we're also offering what we call HAPS IP prototyping kits, which are daughter boards with example designs that allow you to very quickly start developing your software drivers. Okay, so once again, EP-ready solution means emulation and prototyping-ready solutions. What differs? We have a common hardware for both emulation and prototyping, but what is different is the software stack. So in the case of emulation, we would be using ZeBu software, while when doing prototyping, we would use HAPS protocompiler. So the big difference is that ZeBu software is here to allow very fast compile time, to allow you to have maximum visibility onto your system running on the emulator, and to be cycle accurate in order to be able to reproduce issues that you have found. When we talk about prototyping, we talk about asynchronous clocking. Okay, we are not based on a master clock, so in that case, you would have asynchronous clocking, and the software is tailored for performance. Okay, so we want to run at speed, talking with real-world interfaces, and that's why we have a different software stack to adapt to every use model that the people may want to use, either prototyping or emulation. So what are the trends and challenges in terms of prototyping? So we see design sizes are varying quite a lot. You need scalability, software complexity, and you want real-world interfaces. Okay, so that's really specific to prototyping. You want to talk at speed with the real world. So top challenges, well, long software workloads, you need really high performance, and you need to have debug. So you need sufficient visibility inside your FPGA in order to debug it. Most of the time, prototyping is going to be used to do software development, okay, when emulation is rather used to find early RTL bugs and to do also hardware and software co-simulation. But when you want really to test your software, prototyping is going to run a lot faster. Okay, so here is our solution. So it's called HAPS 200. So you'll see that with the emulation product, we're talking about the same hardware. It's presented in a rack. So here you can see this is one given module. So these are the HAPS 200 modules, which are based on 6 FPGAs. You can go from 1 to 6 FPGA. These FPGAs are VP1902, so it's the largest FPGAs on the market. The goal is to avoid to reduce the amount of partitioning that is needed when you put a big RTL onto several FPGA. So you have less partition, you will gain in frequency. In terms of runtime performance, HAPS has been there for quite a long time, and we provide super fast performance at runtime. So this is really what we bring, and versus the previous generation of apps, we see that we are 2x faster than previous generation. We work also on compile time, so the complexity of the new AMD FPGAs has been multiplied by 2, and we're working on the compile time to get to the same level as with previous generation in compile time. Improved debug performance, so say we have a better bandwidth to get the waveforms out of the FPGAs. And then it's backward compatible with previous versions of apps. So these apps prototyping systems are using the same connectors as previous HAPS 100, so you can interconnect your older system to the newer systems, okay, and have some kind of hybrid prototypes. Scalability, okay, from single FPGA up to 10.8 billion gates. So we're talking about really big designs. Okay, so one key difference is that the new AMD is twice the capacity of previous generation. Okay, so that implies less partitioning, so better performance. So we have a nice quote from NVIDIA, okay, from Narendra Konda, who is vice president of hardware engineering. And in their case, they were really early adopters of HAPS 200. HAPS 200 was officially announced in February this year, but we had some early adopters. And so Narendra is stating that he was able to reach for one of his GPU 50 megahertz, which was exceptional compared to what he expected. So he was very pleased with the performance results that we got out of HAPS 200. Okay, when we talk about emulation trends and challenges, so it's not that different. The main difference is that instead of having real world interfaces, we are able to address various use cases like power analysis, performance analysis, virtual co-simulation, software hardware simulations. Okay, so the use cases are different. Design size can vary greatly. Okay, once again, you may want to work at IP level or at SOC level, and you need performance and capacity scalability. So the top challenge are to address the long workloads with the performance, gaining full visibility onto the design which is implemented in the emulator, and allowing to do many iterations per day in order to adapt to an RTL change. So here, that's our ZBoot 200. Okay, so hardware, even though it doesn't look exactly the same, the main difference is being the door in front of the rack. Okay, and the reason for that is that when we do emulation, the cabling is predefined. Okay, so you have a cabling which is performed for maximum flexibility and to let user implement any kind of designs into our emulation solution. So hardware is exactly the same, so no surprise you find the Versal Premium VP 1902 FPGA. Runtime performance is also improved because of the size of the FPGA. Capacity goes up to 15 billion gates. Faster compile time, and the debug bandwidth has been improved also with this new generation of FPGA. So here we got a quote from ARM. So ARM, they are developing their compute subsystems, CSS, and they are deploying these IPs to their customers, and they are using ZBoot 200 as an RTL early verification down to up to HAPS 200 when they need performance, basically. And we got this quote from Kevork Keshishian, Executive Vice President at ARM. Another quote from AMD. So we are partnering with AMD. So AMD is providing us not only the FPGAs, but also the software. So we have a close relation with AMD in order to customize their Vivado version in order to accommodate the needs for prototyping. Okay, so we have this very close relationship with AMD, and that's what leads to extremely high performance. Okay, it's this joint work that we do with AMD. Okay, prototyping and emulation challenges. So we have flexibility. You can adapt to use cases. You may want to have many different platforms, scaling from small to big. And we have this EP-ready hardware, which is the same for both emulation and prototyping. The goal of all of this is to reduce, to have the best return on investment, actually. Okay, so that's and to reduce the price of ownership. Okay, so let's see how we can do that. So Synopsys EP-ready hardware, extended simulation, emulation, and prototyping-ready hardware, one hardware platform. It's configurable for emulation or prototyping. You cannot do both at the same time, but you can do one or the other. And you have two software stacks which adapt to the use model, depending whether you want to do emulation or prototyping. Okay, so it addresses all emulation and prototyping use cases, optimize the return on investment, the goal being to get the most out of your budget and eliminate the need to decide upfront if you want to do emulation of prototyping. You will be able to do the same, both with the same hardware. Okay, so here we see an image of the cabling that we have. So in the case of emulation, we have a very repetitive kind of cabling in order to create some symmetry for the interconnection. And the goal is to be as flexible as possible for any kind of design that you would want to implement. And in the case of prototyping, the cabling is done by the user and it's tuned for performance. Okay, so if you need more connections between two FPGAs in your system, you would want to add extra cables between those two FPGAs, for instance, the kind of changes that you have. Okay, we got a nice quote again from Sci5 adopting HAPS. Okay, so Sci5, they are doing RISC-V CPUs and AI core IPs, and they are using HAPS 200 to do their prototype. And we got this quote from the VP of Platform Execution at Sci5. Okay, another quote from AMD. So AMD are also using to develop their own ASIC. They are using our solutions for their own need. So we got this quote from Alex Starr. Okay, so let's talk about configurability for EP-ready hardware. So same hardware, once again, will allow you, oops, I'm going too fast, will allow you to do either prototyping or emulation. Both use interface memories. Here in the middle, you see the latest. So that's the 6 FPGA version of the HAPS 200 module. Okay, so you can stack them into a single rack. Okay, software stack is different. ZBoo software or HAPS proto compiler. And on one side, you would have the emulation use case, while on the other side, you would have the prototyping use case, such as reinterfacing and certification, for instance. Okay, so this slide is showing how you can take advantage of your hardware resources throughout different projects that will run in parallel. So for instance, you have project 1 doing RTL verification and performance validation. To do that, it will require maybe 6 racks of emulations and 2 prototyping. So this is to do IP and system compliance. Okay. You have a second project which requires two emulation racks to do RTL power validation and 4 prototyping racks to do software bring up and hardware software co-validation. So as the time goes, once you finished what was needed on project 2, you can reallocate your emulation systems. And since it's the same hardware, you can allocate it to your prototyping track and start your software bring up and subsystem with software. Okay, same hardware being used. And then project continues and different needs allows to reallocate your hardware, and your hardware again can be reallocated for any track. It can be the emulation track or the prototyping track. Okay, so configurability. So we have all the different use cases. Early RTL verification, that would be for emulation. RTL regression, that can work for both. Software bring up, software hardware validation, performance analysis, that is unique to emulation. And then compliance and certification when working with real-world interfaces, that would be prototyping. Software stack, we've discussed that already. On one side, you got the ZIBU software. The other side, you got HAPS protocompiler. Debug, when it comes to emulation, you want to have full visibility of your RTL while the application is running on the emulator. In the case of prototyping, we have several techniques to have high visibility, but we don't have full visibility at speed, at least. We can have full visibility, but at a lower speed. Runtime, well, you want to be able to use different kind of hardware. So you want to be flexible and to be able to relocate the design you're testing on different emulation platform. In the case of prototyping, it's design dependent because of the cabling between the modules, which is specific to your design. Okay, major difference is emulation is synchronous, cycle accurate, and when we're running prototyping, we are running asynchronous clock, and we're trying to get the max possible frequency you can get out of each clock domain. Okay, in terms of interfaces, we got memory models, got transactor models, speed adapters, and IP prototyping kit. So depending on the model of the memory, we may have something or not in prototyping. We have everything when we do emulation. And what is specific to prototyping is the IP prototyping kit that provide a working solution for complex protocols. Okay, and then the hardware platform. Cable setup, optimized for flexibility on one side and design dependent on the other side. And that's pretty much everything. So that will be my last slide. Okay, so this is a summary of what we've seen today. You see that so it's called the EP emulation and prototyping ready hardware. The main message is single hardware to do every use model. We have the previous generation of EP ready hardware, which was ZIBU EP and HAPS 100. We've introduced HAPS 200 and ZIBU 200. And for capacities which are larger than 10 to 15 billion gates, we jumped to the ZIBU server 5, which provides a much bigger capacity above the ones from EP ready solutions. So thank you very much. Do you have some questions? Okay.
Anybody on the live stream with any questions? All good on the live stream, folks. No questions.
Thanks for your help, Chris. So I'd just like to say a massive thank you to our sponsors, our speakers, Rolls-Royce as well, our FPGA steering group who are in the room somewhere, and our partner Mike's here as well. So, and the team at TechWorks for helping put on a good event. I hope you've enjoyed it. As you know, we're a member organisation. Without the help and support of our members and sponsors, events like this would not be possible. So again, a massive thank you to them. If you're not a member and would like to become a member to get more great events, then please reach out. We've got a few events here. Gunny can talk about his AESIN conference, which is next month. We've got a town hall for IOTSF, and we've got the verification futures, which is in the 1st of July, which design and our other network community TechWorks AI have got 2 tracks on. So we've got an FPGA track and we've got an AI design IP track as well. So if anybody's interested in speaking at them, you've not already signed up, interested in it, I'll send you out the details. Gunny, if you would like to say a little bit about your conference as well.
Thank you. So yeah, our conference is at the British Motor Museum. It's a very prestigious location right next to Jaguar Land Rover and Aston Martin on the 19th of June. And the themes, we've titled it From AI to Power. So we have a number of streams and they're looking at AI, of course, software-defined vehicles. I think there's something was mentioned earlier about software defines everything. Software-defined vehicles is a big topic. We have a stream on power electronics and AI, of course, can't be remiss. So a great selection of speakers from OEMs like Jaguar Land Rover. We're also trying to get Aston Martin on stage as well. And we have representatives from BMW coming and a whole selection of speakers from the supply chain. One really important area we've focused on is future talent. So we've got a session looking at future talent. We've got some young speakers coming along, talking about their experiences in early career researching. So we can really talk about how we can bring a more diverse audience to our industry. So the event, if you go to AESIN.org, you'll see there's a link to the conference registration. For members, of course, it's free. For non-members, there's a nominal fee. It's only £99. But if you do want to come, reach out to me and I can see if I can get we've got a handful of 2-for-1s available still, so I can make them available to the audience here as a special thank you for being with us today. So yeah, thank you very much, and we'll hopefully see you soon again at a future event.